Guys, it's time. Without further ado, we'll get it started.
But I want further ado.
Alors, bonjour à tous, merci d'être venus ici. On est vraiment heureux d'avoir vraiment rempli la salle. J'ai l'impression que on est juste à la capacité parfaite. On est plein, mais on déborde pas. Puis on a été capable de mettre beaucoup de monde ici. Merci à tous d'être ici. Je m'appelle Mathieu, je suis data scientist chez Intel Security. Il y a plusieurs personnes ici qui travaillent avec nous. Mathieu, Megan. So that's just, in case you want to go to the bathroom, you've got to talk to those people. So there's the two codes here, and you need a badge to get back in. So ask one of us. And
we'll have a break between the talks.
Yeah, we'll have a break between the talks. So bathroom is done. Drinks, we've got a lot of drinks, so help yourself. We've got pizza left. And then, so yeah, one thing I wanted to talk about is, so how many of you are new at Montreal Data? First event. Wow, that's pretty good. Pretty interesting. So yeah, the main thing we do is organizing events, but we're also trying to connect the nodes in the community in Montreal and have organization talk to analysts, well, anyone in the data world. And one of the initiatives that is led by David is our bulletin, our newsletter. Donc, on envoie toutes les 2 semaines une newsletter qui, son objectif, un bulletin, which is working in both languages, so that's pretty good. En fait, l'objectif, c'est vraiment d'amener des nouvelles de la communauté, donc des blog posts qui sont postés par du monde de la communauté, des nouvelles sur les compagnies, poster des jobs qui, donc, toujours autour des données, et vraiment ramener toute cette communauté ensemble. Donc, si vous voulez vous inscrire, allez sur mtldata.com, et donc vous aurez de quoi vous enregistrer ici. Et puis, je pense que c'était tout ce que j'avais à dire. Je vais laisser Von prendre la suite pour parler un petit peu de ce qui va se passer ce soir.
All right. Yeah.
I guess to recap that in English for a second, articles, interviews, and data, and job postings in the Montreal data community. So definitely, and the events that we have upcoming. So this is the place to stay in touch. So it's a really great interview. I really do think so. You guys have to check it out. David puts a lot of really good time and effort into it, and you can tell. So, all right. I'm going to quickly introduce our speaker tonight here, David, or one of 2 speakers, and to quickly, I guess, overview the evening. So I'm sure most of you have seen already, but we're going to have 2 talks tonight. And then at the end, we're going to have a discussion, because this is kind of the kickoff for what we're calling the Deep Learning Study Club, right? So it's not going to take this format. It's going to be more hands-on than that. So we want to really take the time to get feedback from you guys here in the community as to what you think the best format would be in order to actually, learn and study deep learning, right? So think about that while we're discussing and listening and, in awe and getting an idea of what this thing is all about. Because I'm sure maybe we could do a quick hands. How many people are would classify themselves as beginners in deep learning? Okay, maybe half. Okay, who would say they're intermediate? Cool. Who's from Yasha Bengio's lab? All right, fantastic. We got, okay, excellent. So we really are trying to, take it from, I guess, all levels. So think about how the best way we might be able to do that might be. But I don't want to take too much time on that note right now. So I'll introduce David real quick here. So the topic tonight for David's talk is going to be, convolutional neural networks, like an introduction to, and building a prototype for this this network and this deep learning system on a shoestring budget. So really excited to see what that's all about. If you're interested in more about what David does, he goes by Proofreader Fs, and he does some super cool stuff. So without further ado, let's welcome David and look forward to the talk.
Hey, everybody. Hi. So I work at Viva Canada. It's an insurance company based out of the United Kingdom, but it's got offices in many countries. Canada is a large part of the international organization, so is France and Singapore, some other countries. And so this is, I'm going to show you what introduction pretty much to convolutional neural networks. The chairman of the global company gave a challenge for a couple of teams. One of them, and by team I mean one person, like me and someone else in the UK to separately or together. We decided separately because I don't like British people. To come up with some ideas as how we can use like the data that's in images. We get a lot of images, of course. You get pictures of accidents, pictures of houses when you want to, pictures, all kinds of pictures of damage of any kind. Some like frameworks where we could use images to help the business. So my knowledge of deep learning was extremely shallow, ironically. So now after this, I'm a little better, but still, if you have any really complicated questions, I'll pass you to my boss, whose thesis advisor was Joshua Bengio. So, right, that's true. Okay, so, like, you know, I'm my title is senior data scientist, so I work with data, as everyone, lots of people work with data, and when most people think of data, they think in terms of tables, which are, you know, nice and structured. You've got your columns, each one of them has a variable, and you've got your rows, each one of them is an observation, and hopefully they're relatively independent. So images are data too, but everything else, that idea of tabular data goes out the window. Because like you could describe each individual pixel in several ways. You can give the X, Y position, you can describe its color, its darkness, etc. But each one is interdependent with all the others to give the semantic content of the data, and in a complex way. If we change a position, if we just like shuffle it up a little bit here, we no longer have something that we would recognizably have an image and want to classify. So position matters, but not that much. If we just move things over a little bit, we want something that's going to recognize, hey, these are the same thing. Or if we change to a different guy, we want someone to be able to recognize, okay, that's a head, and this is a body, and that's, you know, like a foresty background, those kind of features. So this whole idea of working with images, the problem has been humans are really good at figuring out images. We're made, especially human faces, we're biologically designed to discriminate very quickly, but like one at a time. And computers are good at processing vast amounts of information, but not so good with the images, with the unstructured data. So before we go on, does anyone have a guess what this picture is of? I'm sure it's from. All right, well, it is, someone say it, I don't want to say it. Yes, Barack Obama. And if you think about it, you came to that conclusion with just a little bit of information. I think it's pretty pixelated, but there's things like his posture, the fact that I would have a photo of someone and ask you who it is, so it's obviously not your Uncle Ben. You're Spider-Man, you have an Uncle Ben. So there's all kinds of information you instantly process to be able to get that out of relatively few cues, so well done. So what has happened in the last few years is a revolution in this whole idea of image recognition with the technique called deep learning, and specifically the use of convolutional neural networks. And if you want to describe what this does in one sentence, it's you take this your unstructured data and you really create tabular features where you have the deep learning creates features, and then every image would be a row, and it would have values for each feature, and you can use that to do classification. So here's sort of a little toy example of what convolutional networks do. It's if any of you have used Photoshop, we convolve an image. If you use Photoshop, blurring is convolving, so is sharpening an image. What you're doing is using some sort of function to use to take each bit of information and change it according to its neighbors. And you do that over and over, and you do several different operations. And what tends to come out are these really high-level features that these properties of images. Edges are a big one because it's very easy to convolve and see an edge. If you move everything over a little bit, you still get that nice separation. So it's pretty good with edges and with kind of blobby, globular shapes. So the idea here is you take, as I say, take your original image. So this would just be one of many, and feed it through many layers of a neural network. So at first, you're gonna convolve them and find all of these different. This is from like each one of these dots is an image. So this would be one of the dots, and you've got all kinds of them. And so when we've run all our images through, you find what they have and what kind of features they have in common. And you can see most of them are edges in different parts. They'll be in different parts of the image. And then with different layers, you can start putting them together. And you see what happens here? You've got these together, and then the last layer, you get these things that actually were just built out of these small building blocks that were torn apart from this, and they look a lot like what went in. We call these eigenfaces. Okay, and when you want to discriminate, why don't I turn my speaker off? Oh, hopefully I won't be interrupted again. Sorry. All right, and if we want to discriminate between a lot of different kinds of images, let's say we built a neural network that we want to discriminate between faces, cars, elephants, and chairs. So we take all of our images, and you see they're all broken down into the same building blocks. But then when we know the labels of our image, we can build them up, and you can see all of these different building blocks start to be built together in things these eigen elephants. I just made up that word. Eigen cars, eigen chairs, and eigen faces. So it looks like it's incredible in magic, but there are some drawbacks. It's incredibly computationally intensive to build your own convonet. It takes usually a GPU and many, many hours of time. It can be luckily, a lot of it can be done in parallel. One of the big hurdles is that you need your label training data. Like if we're building this thing, we need actual pictures of faces, cars, elephants, and chairs labeled as pictures, cars, elephants, and chairs. And that's not a trivial task. There aren't just reams of labeled images lying around. There are some, but ones for your specific task not exist. And finally, like telling elephants from chairs is a relatively simple task. There's lots of different neural nets built around the ImageNet database, which is what I ended up using, you'll see. And like they can tell kittens from guns, really easy. But I mean, if you try to tell a calico kitten from a different kind of kitten, that becomes a lot harder. You need a lot more training examples. You need your labeling to be really good. And like if people tend to take pictures of black cats a little farther away or to the side because they're superstitious and afraid of black cats, that's going to be a hidden feature you're going to get in there. And if someone takes a picture with a different composition, it takes a lot of images to disambiguate it. Here's an example, like here's pictures of 2 car accidents, but like it would take a lot of examples to figure out that these are of the same thing and that this is the part of the car we're interested in versus that, just because the composition is so different. Parts of the car are blocked off. This has sky, this has other cars, this has some dude in the background, there's a road, etc. So the challenge we were issued by the chairman of Aviva was to determine from the image of a house its layout, so if it's a bungalow, if it's a 2-story, if it's a row house, that kind of thing, and its surface for fire protection. That matters a lot, whether it's brick, whether it's stone, and different other surfaces. So these were going to be very similar images. So that's a problem. We need a lot of training data. And the first problem, challenge number 1, is where are we going to get these labeled images of houses? And so I kind of thought a little bit about outside the box. I used Google Image Search and Amazon Mechanical Turk. I'll explain how I did that. So I just did a Google Image Search for all the things I wanted. So brick house, for example. Yeah, you see it. I'm getting to that. I searched for brick house, downloaded all the images, and labeled them brick. Of course, you got a problem is that Google Image is, not very precise. You're going to get a picture of the Commodores, who had a 1978 disco hit called Brick House. Everybody know that song? She's a brick house. That one? All right. So, and that's kind of an extreme version, but you also get like weird stuff, like, pictures of people whose name are brick house. I don't know, but you get the architectural designs and stuff, or drawings of houses. So we had to, like, this is gonna be tough enough without having a nice image set. It would have been pretty much impossible. So I used Amazon Mechanical Turk. If you don't know it, it's a bunch of people who work for ridiculously small amounts of money, and surprisingly, they're all Americans. They don't allow non-Americans to do that. And you set them these human intelligence tasks. So I would take like a grid of 16 images, and I would say, click all the ones that aren't pictures of houses. So they go, okay, Commodores. And so that actually worked out pretty good. The Mechanical Turkers removed all the unwanted ones. So I paid the Mechanical Turkers about $200 and ended up with 3,000 well-labeled images at the end, which wasn't enough. But I was sneaky. I built another convnet just to separate, based on those training images, to separate houses from non-houses. And that's an easy classification task. So I could get a labeled set of about 20,000 images. These things are huge. They take a lot of time to train. I tried to build my own, and I came across the realization that these things are, how you set up all your layers and everything is very sensitive to that. And I just didn't have the time. They weren't paying me full time to do this little challenge, although you should. So what I do, I use a pre-trained CNN. Now this is cheating on my budget, because this software I used costs $500 a month, but I didn't have to use it. It's just we had the license and it did it, so I used it. Why not? But there are all kinds of things. Keras has a really good implementation of ImageNet. So yeah, I used software used to be called Dado, and they suddenly changed their name to Turi, and then a week later announced they were bought by Apple, so I don't know what's going on with them. But they had built this convnet based on ImageNet, and the ImageNet's been around for a long time. It's like 1 million something images. It's very hard to find. There's academictorrents.net. There's like one guy who's seeding the 1.2 terabytes of images on there. It's really, actually, I don't think he's seeding it anymore, so it's really difficult. And it's got like, it's very unfocused. It's like pictures of thousands of different categories. But for a general, just pick features out, those edges and everything out of images, it was a good place to start with. And then what you could do is feed in your own image sets into the last layer and get a nice classifier, except I didn't do that because I was even lazier. So I don't know if I wrote this on a slide. So what I did is I just took the features that their ImageNet thing spat out, and I just built a simple logistic regression classifier based on it. So it's not perfect, but it works reasonably well given the tools. And so the last challenge that I faced in this whole project is how to deal with the anticlimax, because everything was pretty easy. I thought that was a good joke. It was my timing. You know what the secret to good comedy is? Ask me, what's the secret to good comedy? Okay, you ask me. Timing. Okay. The slide. So the CNN gives us the features. My logistic regression classifier uses the features to give class probabilities of all the different labels. So you want to see what I did? You're supposed to say yes. Okay. Sounds terrible. Okay, so we're going to do like 2 layers of abstraction here. I've got to RDP into my work desktop computer in order to RDP into my work server. So hopefully this will work okay. Oh no. My screensaver is not black.
All right, who's got another joke around the
I got a Star Wars joke. What's the temperature of the inside of a tauntaun? Lukewarm. Okay, I'm going to reconnect. This always works fine at home. Okay, everyone knows my employee ID now, but you do not know my password. But you know how long it is. Okay, so who here knows Montreal, like the neighborhoods and everything? Someone, okay. Oh, you're in front. Give me somewhere to go on a map where I could find a picture of where I could find a house. Westmount. Hopefully the world is in my. Oh, come on. What is happening? I think Intel's network doesn't like my RDP. Oh, wait. No, it's frozen. So what I was gonna do is like zoom in on Google Street View, take a screenshot of a picture, and then go to the load it. Oh, does that work? No, it's not drawing at all. It's frozen.
Let's try on
Vaughn, you got your hotspot? Sorry about this, fellas. Pretty sure.
Guys, close your eyes.
Because this only happens when I overload my Wi-Fi at home.
When you're ready, my network should be up.
Disconnect this. Okay. No, it's okay. Okay. YouTube audience, how you doing? Yeah, good idea. All right, so, hello.
We're back.
So I decided not to do the screenshot thing because I think maybe it's that double layer of networking that's going wrong. And while I have you all, I'm going to take a selfie with you guys in the background because that's what I do. This is for my mom. Hi, Mom. Because I haven't given her any grandchildren, so instead I share with what I do in my life, and like data is my children. Okay.
You guys are all.
All right. So instead of doing the screenshot thing, which is really cool, but I'm afraid I'll waste your time and it'll crash again. I'm just going to take one of. I've got a set of images that they're the test set images. They weren't made to build the models, and I'll just run one of those. Or actually, you know, we could do a URL. What's happening here? Yeah, let's do that. That's kind of cool. All right, someone give me a search term for something having to do with a house. But something, okay, eavesdrop. But I need pictures of entire houses. Give me an adjective that goes with house. Victorian house. Oh yeah, because a lot of my training images looked like that. Okay. What's happening? Victorian houses and where Victorians live. Okay. Copy image location. Damn it. Oh. All right, let's see what it, oh, come on. It's not connecting. All right, I'm gonna just take a random image from my test set. It died again. Vaughn, did you move out of range?
No, I said
Okay, well, I suck. Oh, wait, oh. Random image, yes. Okay, so let's see what the image is. Oh, that's a weird one. Okay, so that's the image. I have no idea what it'll have made of that. It put two-story very low. It thinks it's a bungalow. Let's figure out one that's not as weird. Okay, so thinks it's a bungalow. It's actually semi-detached. Well, pretty close. Brick, pretty close. One more. When I did my demo to the chairman of the company, I had a really hard one, and the classifier got it right away. It was such an outlier. It was crazy wonderful. No, no, I did he picked a house on Google Street View. So this one thinks it's a brick cottage. Those are bricks. That's cottage-like. I say it's a win. All right, that's all I got. Oh, is there any questions? Yeah, exactly. Yeah, yeah. Well, actually, each one of them is a separate classifier. Yeah. Yeah, that creates the 150 or so features. Yeah, the CNN. Yeah. Right. 14, I think. But I mean, that's including like a softmax layer and all of those. I didn't even bother. I didn't even retrain the last layer. It was difficult in Dado, and I didn't want to. I assumed it would be easy to, because you pay them $500 a month, but it was difficult to do that. So I just used the features like based on ImageNet. I didn't even retrain it. Right. Yeah, I didn't retrain that last one because I was running out of time. How many? Oh, ImageNet is trained on 1.3 million, I think. Oh, how many epochs? I have no idea. From the Google searches. Well, there's a total of about 20,000 images, but then for each one, about I guess 2,000 for the logistic regressor. And so the two categories were bungalow, not bungalow, and then semi-detached, not semi-detached. Hi.
Wondering if we add another layer to the top to interpret and mixing of
the ideal, and if I could have done it over with a package that makes that easy, is to actually retrain that last layer just based on your own images. That there's Inception makes it easy to do that, but ecosystem on Red Hat Linux, and it was a nightmare trying to get TensorFlow working on that. I just gave up.
What happens when you zoom in, when you zoom out from the center of the picture? You get a probability?
Yeah, I mean, sorry, I left that part out. One of the tricks I used to improve the classifier is to actually crop images, and especially every single one was flipped right, left to right as well. But yeah, you generally get the same result. Yeah. Well, I would say roughly 60 hours, and 40 of those 60s were blind alleys, like trying to get TensorFlow.
Take it away. Let's give them a round of applause.
Thank you. So I recently got pretty excited about deep learning. Started reading on the topic like a month or two ago, and decided to kind of build a more introductory level talk that like show the basics of it and how they're composed. So recurrent neural networks, to understand them, we can start from the basic aspect. So they're essentially a regular artificial neural network. So there are basically cells like this that are layered on top of each other. And the particularity that we need to pay attention to is a little bit like we saw in a previous talk, where every input is connected to a different value. So in this case, we have a 3x2 with a hidden layer in between. But if you connect an image to it, usually you take the entire pixels in that image, you flatten them out, and you enter them in the input layer. And then you stack them up. You have a hidden one and an out one. And then you have a prediction or something that that comes from there. If we take a look at one single cell, the most basic aspect for machine learning is a linear regression. And that's the process by which you're trying to find the single line that passes as close as possible to all the points in your data set. So if you're trying to predict like a traditional machine learning classifier where you take house prices and you're trying to predict, okay, how much does a house cost that has 5 rooms, 2,000 square feet, and so on, you would put that and try to find that line that crosses all those parameters. So, but if you want to represent more advanced equations, you have to break away from the linearity. So in neural networks, you have those activation functions. which is the purpose of introducing something nonlinear, because if you add linear equations together, you end up with something linear, and then you don't have a network capable of representing something nonlinear. And it also binds the function between two values. So depending on which one you use, you're either going to get a value between 0 and 1, or between -1 and 1, for example. And you usually want to control the kind of output that you're getting. So to make it deep, you start with a small network and you add layers on it. So you start with a small network like this, and by the time you get decent results, you pretty much look like something like this, where each of those is a function. So that's one of the reasons why they're hard to train, is there's a bunch of parameters where you have to compute all of them, and you end up with so many layers. Neural networks are good, but they're limited when dealing with sequences because they have fixed size input and fixed size outputs. So if you're dealing with language and you want to either understand some sentences or you want to label images and try to say what's in there, you need to generate multiple words. So to solve that, there's a different type of neural network called recurrent neural nets, and recurrent, also called RNNs. They have the particularity of having loops between them. So instead of having an input and an output directly, they also have a hidden state that loops around. And it's a little easier to understand when you unroll the loops like this. And what makes it very interesting is that every little square named A has the same way. So you're essentially training a single cell with some hidden state size and some parameters. So if you were to take a sentence, you would start and you would feed in each word separately at every input. And if you want to with positive or negative response, then you can have your classifier. But there are some problems with just pure neural nets or pure RNNs, and that's with dealing with long-term dependencies. So if you have a text and you need some cells to remember specific features in the past, like the gender of a pronoun, and you wanted to use it later on, then it needs to be able to remember sentences or like relations that go deeper than the size that you're passing as an input. So long short-term memory cells is a pretty classic solution to that problem. And it modifies the original neural network cell by adding a few more gates. So you have a forget gate, an input gate, and an output gate. So at every input, the neural net decides how much of what I know right now should I forget, how much of what I just saw should I learn, and what should I output based on the two previous conditions. And it solves some of the training problems, because when you're doing a gradient descent on an RNN, then you can have vanishing gradients and floating gradients, and LSTM usually solves all those problems. Once you have a recurrent net, you can organize them in various ways. So you can either have a one-to-one or many-to-many or one-to-many, depending if you want to predict a sentence based on a single value, or if you want to predict a single value based on a sequence. One good example, and one blog post that really sparked interest into recurrent neural net was one by Andrei Karpathy, where he wrote an article called The Unreasonable Effectiveness of Neural Net. And the example that is used is that he's training basically a character model. So character by character, when you feed it text like Shakespeare, for example, it will try to predict at each character what the next character would be. So the encoding format looks like something like this. So you have at your input layer the characters that are being inputted to the network, then they go through a hidden layer, and then finally to the output. The encoding here format that's being used is called one-hot encoding, is when you have a single dimension in your vector with a 1 with the current class that you're inputting, and you have 0 at all the rest of the positions. It gets very useful when you have a prediction. So if you see here, we predict the letter O. And if you look at the value for O, it's much higher than the rest because of the input of the output of the network. There's some examples of that. That is one of them that was one trained from Shakespeare. So all the syntactical formatting or white spacing is all coming from the RNN. So there was no title, there was no colon or anything. So you guys can probably read that, but we have sentences like, alas, I think he shall become approached in the day when little strain would be attained into being never fed. So you've got basically gibberish text, but that's still really well formatted. And those networks are, like if you check his blog post, it's linked a little later in the slides, you'll see examples where it's been done on XML data and even on LaTeX data, where it produced a research paper on geometry with actual shapes in it. It's pretty interesting. But why stop at text when you can go and look at code? So looking in software, if you're trying to predict the output of a, or actually you try to predict basically a whole function or a whole file, this was trained on the Linux kernel plus glibc. And you can see that the neural net by itself outputs comments and outputs valid sentences, or actually English-looking sentences. The code is syntactically valid, but it's not semantically valid because it's missing variable declaration and stuff like that. But like at first glance, as a developer, you look at this and say, oh, it looks like real code. And they get some really funny results. Like indicate policy, like that sounds like something that you would see in Linux. A little further there was an example on how to visualize RNN cells. So when you take your entire stack of pancake layers, you get so many cells, and you can look at one of them in particular and try to find interesting patterns. Here, some of them were sensitive to the position in the line, some of them reacted to quotes, some of them reacted to being inside the if statements. So you can sort of throw some text at it and then inspect the different cells and the inner state to see what they react to. I find that pretty fascinating. So key takeaways, neural nets or recurrent neural nets are basic neural nets. There's some open documentation, and I'll post those on Twitter after, so I'll have to take them down. The first class on CNN actually starts with a really good introduction on neural nets and what composes cells. It's a really good intro. Cola's blog, Understanding LSTM Networks, is where most of the loops and unrolled loops images were coming from, and he has a good mathematical example of it so that you can follow step by step, and it goes into more detail of different types of CNNs that are available. And last but not least, the anti-cavity blog, which was the example that we used. Since this was going towards a study group, I thought that sort of a dissection of a paper that I found interesting lately, and that is a good example of how you can compose and get interesting results with existing algorithm. So the neural talk one, or actually deep visual semantic alignment for generating image descriptions, is basically a way to assign labels inside an image and to point out all the objects. So starting from a high-level perspective, we're starting with an image recognition CNN. That one was trained on ImageNet, so the same network that was used in the previous talk. And again, this basically uses all the lower layers of ImageNet, because there's a neat trick you can do, because all the basic features, all the edges, and all the not so complex features are at the lower layers. So you can take these lower layers and train your own model on top of it. And you get actually pretty good results. They use a bit of a different approach. They have a regional convolutional neural network. So they basically scan the image in a novel way. And they found out regions that score the highest for different categories or labels. And then they can take the top 19 regions of an image and do further processing on that. Once you have an image or an image recognition, CNN, you can feed that to a recurrent neural network. And in this case, they use a bidirectional one. So that's one that also feeds from the future as well as the past. And they're stacked on top of each other usually. And you can start predicting words. To start predicting words, usually you need a good mathematical description of a vector space that really represents word semantics that we're used to. There's a paper called Word2Vec that basically explains how to do something like this. So you take, like in 100 coding, if you have 9,000 words, you basically have 9,000 dimensions. So you take those 9,000 dimension vectors, you feed them through Word2Vec, through a special process, and you're going to get a much lower dimensionality vector, in this case about 300. And this will have interesting properties that they will respect the semantic and statistical analogies that are coming in the word. So the network is trained so that words that appear at the same words are located closer together. And it gets interesting because you can do operations and vector math on it, and you can convert back to embeddings and back to words. So you can do things like puppy minus dog is approximately equal to kitten minus cat. This is one where it actually does puppy minus dog plus cat, and you get kitten, or in the embedding space. So this gets a really kind of deep knowledge or a feature space that makes sense that you can reason into, because now you can measure distances between words in a Euclidean space and be really flexible with it. It's a little summary from the training process. So the dog leaping to catch a frisbee is inputted to the RCNN. That outputs embeddings on the left. And at the bottom, you have the recurrent neural network inputting the text. And you have a shared embedding space. And that embedding space is basically being compared, and the cost function is being set to be the sentence score. So basically how close those two embeddings are. So the network is actually being trained to learn its own intrinsic representation of a feature vector that both matches the image and language generation together. And you throw more images at it, and at some point, it learns how to speak. Text generation needs a bit more details. We have like start tokens and end tokens that we add to make sure we bound sentences, because if you just ask an RNN to predict something, it will predict something. It doesn't know when to stop, so you add a start and a stop sequence to actually get a bounded sentence. If we look at some examples, these are good examples. We have a man playing accordion in a public area. On the right side, we have a woman in a white dress standing with tennis racket. Two people in green behind her. That's really interesting. It found a different person and actually composed a sentence with a different road group that was representing what was in the image. It also fails. Sometimes it fails in very funny ways. Like this, you get a young boy holding a baseball bat on the left. And on the right is one of my women holding a teddy bear in front of a mirror. So you can find the code on GitHub on Carpet Neural Talk 2. And this is the refactor version that's running under Torch. It's a little more optimized for the version. And there's a bunch of examples on the site that was done on the previous slide as well. So check it out. I believe I can try to answer some questions.
So in the neural talk example, is the image just fed the first time step, and then it's just the context of the previous word generated?
Yeah, so the image is fed at the beginning and then generates the embedding space. And the embedding space is fed with the start token in the RNN, and then that feeds on. So we use he uses beam search to find out the next word. So you just scan for the highest probability word, and then you just feed, and then until you get the end token, and you repeat the process. You don't need to repeat the image because the image always gives you the same output in the neural net.
Sorry, just to clarify that, so you have the image, and the image gives you a list of words.
The image gives you a feature vector, which was the embedding, which basically is similar to the first. No, not exactly. It gives you a certain feature vector plus that you add to a start token, and then you can use to start generating words. So it sort of gives you the hidden states of the beginning of your sentence, from what I understand.
So for instance, in the basic example, with the output from the image part of the neural network, the baby, baseball bat.
The output of the image part does not really correspond to words. It's just a feature vector that's inside.
What tool do you use for RNN?
So I've been reading the TensorFlow source code kind of extensively and kind of comparing it with the papers on LSTMs. Some of the sequence-to-sequence stuff on the TensorFlow tutorial are actually pretty good. They show you how to do machine translation when you feed it something insanely big, like 20 gigabyte of text in those languages. And then you can enter qui est le président and you get who's the president and the output. A lot of the examples that I saw were using Torch, which is a Lua-based framework. But I personally like TensorFlow because of the multi-machine and GPU. Well, all data frameworks also have GPU, but TensorFlow provides Docker images. So if you want to train like an Amazon, you can use a GPU instance that you can get for, well, they're not that cheap, but you can do spot pricing. So they'll give you instances when there's no demand at like a tenth of the cost. And then you can just load your image. So when you start that project, you basically import the TensorFlow Docker basic, and then you just write your own code and you can deploy it. But you still need, like, I was attempting to learn LSTMs or RNNs without going into like all the stack of papers. And at some point you're watching the code, you just see a bunch of letters being, and then some vector and matrix arithmetics, and you need to go and compare. So spend time looking back and forth. But yeah, TensorFlow. No, I've looked at Keras, but I mean, I'm beginning in that field, and I find that like a lot of the frameworks that try to make it easy to experiment with kind of hide all the details that you need to know to understand how your model works. It was the same thing when I started being interested in machine learning. You try doing scikit-learn, and you're throwing a big matrix or a big vector of things, and you don't know what those numbers mean. So I'm thinking going through TensorFlow as first is going to give me the knowledge to actually then move to different frameworks for experimentation and to still be able to debug. One thing I like about TensorFlow is that you can have a tensor board. So you have a JavaScript UI that can basically inspect the contents of your neural net. Solana I was taking an example of remailing TensorFlow, and I was adding variable scopes everywhere, and that makes pretty boxes around the different parts of the code and follow. This is the input, those are the embeddings, this is the classifier, this is the sequence part of it. And Keras can actually be set to use TensorFlow as a backend. It uses Theano as a default. But if you do use TensorFlow with Keras, then you'll see the same kind of visualization, and you'll be able to use a UI tools that come with TensorFlow to inspect the training process of your Keras network. So you can get things like histograms, it's going to tell you how your loss function is doing, and it's going to give you a pretty graph view of your model.
Internal state is found to have the same number of units as output. Whereas in the example that shows you have like 3 units for the input internal state, but the output can be one encoding. How long have you ever used it? Like
you can have a different. It really depends on what kind of implementation you use. Like for example. Yeah, but what I mean is. Yeah, I want to give you an example on this one. Actually, so recurrent neural networks, I don't know what Keras does, but I know TensorFlow tries to abstract RNNs and give base classes and tell people that they can use different implementations. And one of those things is STM, one of those other things are GRUs. But in the default recurrent neural net, you have the output and the internal state basically being the same line that crosses over. In the LSTM, you have a different output and you have a different internal state. So you have an internal state size that gets passed along to the different layers, and you also have the output that's being passed around to the different cells. Sorry. But in the example that I've seen, even if you have a big internal state, they usually have a dense, fully connected layer on top of the recurrent neural network, and then you generate 100 coding based on that. No, not there yet. But in the literature, usually they try to keep it as low as possible, because the more internal state you have, the risk of overfitting your model. A bit longer to train as well. So you try to get as little as you need to complete the task. And have the interest. Yeah.
You have much experience with deep RNNs?
No. Yep.
If you have a power map describing the scenario, not scenario level, but country stuff, and draw it.
That would be interesting. Not with an architecture like this. There is some pretty interesting development in what they call adversarial generative network. And that's some architecture where you have one network trying to generate pictures and the other network trying to discriminate, is this fake or is this real? And they give out pretty interesting results. You can look at like TensorFlow generative networks to get examples of kitchens being generated or faces being generated without actual training data. I've also read autoencoders could do something similar, but I don't know less on the topic. Yeah.
I guess on a similar vein, if you have a paragraph that describes, let's say, a mathematical formula, can it come up with a formula?
That would be interesting. So there's a paper called Recursive Neural Network, which they're trying to find an acronym that's not RNN because it confuses people. But you essentially feed it a tree structure, so like a parse tree. I don't know if that's what Google uses with parsing the parse trace or syntaxnet, but you're able to feed hierarchical structures. And if you do that, then you should be able to do mathematical operations because you can have your operators and then the operands and whatnot.
For recursive neural network, the R, it should be RNN, but then the R stands for recursive neural network.
Yeah, no, I think there's another letter that they invented. I think it's RENN, but like it depends on who you ask. Like you read around, just you look by recursive, and you have more chances of finding what you're looking for. Going back to the drawing, I've seen a, I don't remember if it's an RNN, but essentially the system would predict the position of the pen at a specific moment, and you got a series of XY coordinates, and it would actually draw something. So if you could do that with some sequential neural network, because you all end up with a sequence of points, but then your training data also has to be sequence driven, so you have to record some vector graphics and stuff like that. Yeah, I guess the point is that more features are learned by the algorithm itself, and you can apply it to different things. But this was not a scientific paper based on a specific goal. It was more of an exploration, I guess, that was done.
Typical example you have where it was generating code.
Yeah.
Could the validity of the code and whether or not it's compilable be one of the scoring criteria that I have to generate the code?
But to have something within your scoring criteria, it needs to be differentiable. So the way training works is by computing derivatives of all your parameters, and then you're trying to tend towards a local minimum or global minimum. Semantic validity is very binary, so it's hard to say would that be valid. You would have to come up with, I guess, some structure to try to fix code mistakes and make code valid in itself before you go towards that route.
Raised the point about the surface structure. So recurrent neural net will learn a surface structure. Learn big behavior. So I was wondering whether you really sort of, what processes you had in deep learning model and how to address that. So this idea of getting so that your attempt to learn longer term behavior. So finding that in sort of conceptual planning, getting structures?
Still early in the process to see if I actually find features. Like the thing I'm trying to experiment with right now is to predict compressed audio frames, because I think they have one of the best feature sample for predicting audio. But like they're used for machine translation, so they have to be good at long-term references, because text can go sometimes like a few lines before you get reference to a pronoun, something like that.
We got one more question.
Yeah.
And there's going to be time afterwards.
Yeah, I'm not going to leave right away, so you can stick around. Still haven't had pizza. Don't want to be the last one. Yeah. Sense2Vec? No. Although something that I've seen recently that was interesting in the embedding space, somebody trained an embedding classifier, I guess, or an embedding system based on the philosophy library from the Stanford library. It's called Philo2Vec. You can look for it on GitHub. And then you can do interesting, I guess, vector math on concepts like activism minus ethics, and then you get something really dark. And it's really fun. They give a bunch of samples on the page. Yeah. Nice. Thank you.